Good day. I'm John K.P. Gamboa from BSRTE 2B, and today I will discuss Chapter 3 in Bushong, which is the electromagnetic energy. Of the different forms of energy, electromagnetic energy is unique in that it does not require matter to transfer energy from place to place. Electromagnetic energy is formed when an electrical charge is accelerated by an external force. The acceleration of the electrical field creates a wave of alternating electrical and magnetic fields that separate from the charge and move off into space. This may seem very abstract and might be hard to make sense of. Fortunately, we can discuss the behavior and fate of the electromagnetic energy without needing a full understanding of how it is created by this interaction. The central point is that this electromagnetic energy becomes separated from the electrical field that created it, allowing it to transfer energy from place to place. Even in the absence of intervening matter, once this wave is created, it moves through space until it encounters matter. When it encounters matter, one of the three things can occur. It can reflect off of the matter and continue to move through the space in a different direction. Or it can pass through the matter, also continuing on into space. Finally, it can be absorbed. It is through absorption that the energy contained in the wave is transferred to the matter that absorbs it. Which of these three interactions occurred depends on the specific characteristics of both electromagnetic energy and matter involved. Electromagnetic energy has complicated characteristics, which can be difficult to describe. Some features are best explained by assuming that electromagnetic energy is a wave, while other characteristics make more sense when it is assumed to be a particle. In the context of beginning to understand how electromagnetic waves transmit energy from place to place, describing electromagnetic energy as a wave is useful. Waves occur in repeating patterns. The distance between their repeats is called the wave's wavelength. The number of times the pattern repeats itself per second is called the frequency, and the rate at which the wave moves through space is its speed. We use the symbol lambda for the wavelength, F for frequency, and C for speed. There is a mathematical relationship between these parameters. Wavelength is measured in meters, frequency in per second, then speed, which is distance over time, equals wavelength times frequency. Substituting symbols for these units allows us to calculate any one of these parameters, assuming we know the other two. The speed of electromagnetic energy is constant, traveling at 3 times 10 to the 8 meters per second in a vacuum. So if we know the frequency of a wave, we can calculate the wavelength, and if we know the wavelength, we can calculate the frequency. Electromagnetic energy is present everywhere and exists over a wide energy range. X-rays, visible light, and radio frequency are examples of electromagnetic energy. The properties of electromagnetic energy include frequency, wavelength, velocity, and amplitude. In this chapter, discussions of visible light, radio frequency, and ionizing radiation highlight these properties and the importance of electromagnetic energy in medical imaging. The wave equation and the inverse square law are the mathematical formulas that further describe how electromagnetic energy behaves. Ever present all around us is a state of energy called electromagnetic energy. This energy exists over a wide range called an energy continuum. A continuum is an uninterrupted ordered sequence. Examples of continuums are free-flowing rivers and sidewalks. If the river is damp or sidewalk curved, then the continuum is interrupted. Only an extremely small segment of the electromagnetic energy continuum, the visible light segment, is naturally apparent to us. The ancient Greeks recognized the unique nature of light. It was not one of their 4 basic essences, but light was given entirely separate status. They called an atom of light a photon. Today, many types of electromagnetic energy in addition to visible light are recognized, but but the term photon is still used. A photon is the smallest quantity of any type of electromagnetic energy, just as an atom is the smallest quantity of an element. A photon may be pictured as a small bundle of energy, sometimes called a quantum, that travels through space at the speed of light. We speak of X-ray photons, light photons, and other types of electromagnetic energy as a photon radiation. The frequency range of electromagnetic energy extends from approximately 102 to 1024 Hz. The photon wavelengths associated with these radiations are approximately 107 to 10 to 16 meters, respectively. This wide range of values covers many types of electromagnetic energy, most of which are familiar to us. Grouped together, these types of energy make up the electromagnetic spectrum. The known electromagnetic spectrum has three regions most important to radiologic science: visible light, X and gamma radiation, and R and radio frequencies. Other portions of the spectrum include the ultraviolet light, infrared light, and microwave radiation. Ionizing radiation different from RF or visible light. Ionizing electromagnetic energy usually is characterized by the energy contained in a photon. When an X-ray imaging system is opened at 80 kVp, the X-rays it produces contains energies ranging from 0 to 8 keV. An X-ray photon contains considerably more energy than a visible light photon of an RF photon. The frequency of X radiation is much higher and wavelength much shorter than for the other types of electromagnetic energy. It is sometimes said that gamma rays have higher energy than X-rays. In the early days of radiology, this was true because of the limited capacity of available X-ray imaging systems. Today, linear accelerators make it possible to produce X-rays of considerably higher energies than gamma ray emissions. Consequently, the distinction by energy is not appropriate, and take note that the only difference between X-rays and gamma rays is their origin. X-rays are emitted from the electron cloud of an atom that has been stimulated artificially. Gamma rays, on the other hand, come from inside the nucleus of radioactive atom. Whereas X-rays are produced in diagnostic imaging systems, gamma rays are emitted spontaneously from radioactive material. Nevertheless, given an X-ray and gamma ray of equal energy, one could not tell them apart. This situation is analogous to the difference between beta particles and electrons. These particles are the same except that beta particles come from the nucleus and electrons come from outside the nucleus. X-rays are produced outside the nucleus of excited atoms. Gamma rays are produced inside the nucleus of radioactive atoms. The only difference between X-rays and gamma rays is it is okay. Visible light is identified by wavelength, radio frequency is identified by frequency, and X-rays are identified by energy. Again, three regions of electromagnetic spectrum are particularly important to radiologic science. Naturally, the X-ray region is fundamental to producing a high-quality radiograph. The visible light region is also important because the viewing conditions of a radiographic or fluoroscopic image are critical to diagnosis. With the introduction of magnetic resonance imaging (MRI), the RF region has become more important in medical imaging. The electromagnetic relationship triangle can be helpful in relating each scale on the other two. That's all. Thank you.